Welcome back. In this lecture, we'll talk about the different data types NumPy can support and how changing the type of the variable affects how we see the data it stores. We'll begin by examining the default perception of a dataset if a type isn't specified. Then we'll discuss what kinds of data a NumPy array can obtain, before finally going through some examples. Let's get coding. We'll begin by defining a 2D array, also known as a matrix, called array A. It contains the integers from 1 to 6 divided into 2 rows. If we call the variable on the next line, we'll see an array of whole numbers. That's because the default data type for this function is set to none. As stated in the documentation, this automatically assigns the dataset the minimum type required to store the different values in the sequence. Alright, but what if we want the dataset to be a specific kind? Well, all we need to do is set a value for the data type argument dtype and rerun the function. In a new cell, copy the code we just wrote and add dtype equals. Before we specify the data type, it's important to know what kind of values we can use here. In the beginning of the lecture, we mentioned that arrays can contain numbers. To be more precise, int arrays can contain all the numerical data types supported by C, since NumPy was initially based on that programming language. These include booleans, integers, unsigned integers, floats, as well as complex numbers. Apart from the booleans, the rest of the types refer to using numeric data and thus even have various subtypes, depending on how big each element needs to be, ranging between 8 and 128 bits. To see what we mean, let's set dtype equal to float32 . The output is an array with the same shape as earlier, but this one contains decimals rather than integers. This is because we've specifically told the array function we want the output to consist of floats. That's why even if we didn't have any actual decimal value in our original dataset, all the values turned into floats. The 32 at the end is the size we alluded to earlier. This means that we're allowing 32 bits of memory for each element of the array. Before we move on, it's important to remember that we can't put just any random number at the end of the type. You can use 16, 32, or 64 for instance, so make sure you select an appropriate one. Right. As a matter of fact, there is a second way in which we can choose the data type to work with. Instead of using text written in quotation marks, we can simply set the data type to np dot and the data type. Then, by removing the quotation marks and adding np dot at the front, we get the exact same output. Therefore, the two ways of expressing the data type are equivalent, and we can use either one. As always, good practice dictates sticking to a consistent notation. So just choose one way of expressing data types and stay with it throughout your code. Next up, let's see how NumPy works with complex numbers. Simply paste the code we just wrote into a new cell and change float16 to complex64. We see that every element of the new array is comprised of 2 float numbers followed by a j. This is because the first number represents the real part of the number, and the second one, the imaginary part. Since integers are real numbers and possess no imaginary part, we get zeros as the second value of every element in the array. Hence, even though the output looks different, we're essentially still storing the same data. Okay, we mentioned that an array can also consist of booleans, meaning it's entirely filled with true or false values. Let's illustrate this with an example. In a new cell, here's what happens when we set dtype to np bool. The result is a 2x3 array of only true values. That is because anything different from 0 is equated to true when we're using booleans. To verify this, change one of the values in the array to 0 and rerun the cell. We now see a false value in the same position as the 0, so we're certain how NumPy assigns Boolean equivalents. Fantastic! Lastly, we'll see how NumPy handles text. In a new cell, paste the code we just wrote and set dtype equal to np.str. Of course, this is just short for NumPy strings. The output is again a 2x3 array, but this time each number is placed in quotation marks. This indicates that these are the actual symbols that express each digit, rather than the numeric values we've examined so far. Additionally, at the end we see dtype equal to some combination of symbols we haven't seen before. This expression reads as holding Unicode values of length up to 1. In other words, each element of the array contains exactly 1 character. To conclude, if we substitute one of these integers with a 2-digit number, we'll see that the dtype changes to less than Unicode of 2 elements. This is because, just like with numbers, we have different subtypes of strings, each with a specified length or size. To learn more about the specific types of data we're dealing with, you can follow the external link we've provided in the notebook with this lecture. Fantastic! After learning about the various types of data that can be stored in indie arrays, it's time to explore some fundamentals of NumPy functions. In the next 2 lessons, we'll introduce some of the most useful features of NumPy's functions. Thanks for watching!